problems involving motors. So in this first problem, and by the way, pause the video if you're looking at this yourselves to write down or draw down the diagram here. In this first problem, we've got a coil of wire. Now, in this case, it's not a single coil. We've wrapped the coil around and around and around. So there's actually, in this particular example, there are 50 turns or 50 loops of coil in this winding. So we actually refer to it as 50 turns. And we're going to assign a variable to that. That's often given the capital letter N. So N is the number of turns in the coil of the motor. We've got our magnetic field, our two magnets here. Now take note that the right-hand side is the North Pole, and this is the South Pole of another magnet. And so our magnetic field lines are going to go from right to left. So they're going to head in that direction. On the coil, I've just placed 4 marker points, A, B, C, and D, so that we can refer to different sides of the coil quite easily. Here are the two ends of the coil making contact. So there's a green end, or like a pale green end, and a yellow end. They're making contact with the commutator. So that green, pink, curved parts there, they're the commutators, or the commutator. So if you remember, they're simply think of them as a half ring of copper, and each of those is in turn connected to a battery, and here's the positive side and the negative side. Okay, a bit of data I'm going to give you. So I've already given you the fact that there's 50 turns in the loop. The second piece of data I'm going to give you is that the magnetic field strength B is 0.6 Tesla. Side AB, so distance AB, distance from A to B, is 10 centimeters. Distance BC is 15 centimeters. Pardon me, 15 centimeters that was. And CD, well, that's going to be the same as AB. So both these sides are the same, and they're both 10 centimeters. The battery is supplying a current to the motor, and the current will come out of the positive end of the battery into the coil, around and around and around, and come out this end like this at the moment anyway. And we'll say that current there is, in that direction, the current is 2 amps. So the question is, the first question I'm going to ask you is, what is the value of the force on the side AB of the motor? So what's the total force due to the magnetic field acting on side AB of our winding, or the coil? So that's what we're going to try and work out. So to do that, we need to use a slightly different version to F equals Bill. Remember, to work out the force, it's F equals Bill sine theta. We're not going to worry about the sine theta because this line here, well, this edge of the coil is at right angles to the field, and so the sine of theta is going to be 1. So it's just going to end up being F equals Bill. But because we've got more than just one single length of wire, we've got multiple lengths here, and they're all carrying a current because we've looped the coil. Now, because we've actually gone and looped the coil 50 times, there are 50 lengths of 10 centimeters of wire in that section from A to B. So that ends up multiplying or increasing the size of the force. So if there was 2 windings, we'd multiply the force by 2. In this case, there's 50 turns, so we're going to multiply by 50. So the general rule is to work out the force on the side of the motor, you need to multiply F equals B by the number of turns in the loop of the motor. In this case, it's 50. So if we now plug in our values to work out the force on side AB, we're going to get F equals B, which is 0.6 Tesla, multiplied by the current through that part of the coil, which is 2 amps, or through each of those individual lengths, it's going to be 2 amps. The length of the coil is the length AB, assuming it's all in the magnetic field, and that is 10 centimeters, but we need to convert that to meters. And so that will need to be 0.1 meters. And then finally, the number of turns in the wire, or in the coil, is 50. So we're going to multiply all of that by 50. So if we go ahead and work this out, it's going to be 0.6, it'll be 2 times 50, which is 100. 100 times 0.6 is 60, times 0.1 is 6. So that actually works out to be 6 newtons. So the value of the force trying to act on this side of the motor is 6 newtons. The second part of the question that we're going to ask now is, what is the direction of the force acting on side AB? So what the direction of the force acting on side AB. And to do that, we're going to use our right hand slap rule. So using our right hand slap rule, and we're applying it to this side of the motor, the left hand side, side AB. The thumb points in the direction of the current. Now the current, let's trace it, it's going this way, around through DC, then B, then back through A. So the current is actually running in that direction. So that our thumb is going to point basically out of the page. Our field lines are going from right to left, so our finger's going to point that direction. So our thumb is out of the page, our fingers are pointing in that direction, and if we do that, we note that our force, using our right hand of course, our force must be down. So the force acting on that side of the motor is there. And that means by default, if we look at the other side of the coil, because the current is going the opposite direction on this side, the force must be going up. And you can confirm that using the right hand slap rule if you wish. So from this diagram, we can clearly see that the motor wants to spin in the anti-clockwise direction. So anti-clockwise is the direction it's spinning. So it wants to spin in that direction. So that's an example of how to solve a problem using motors. And most of the problems that you'll encounter are just variations of this sort of problem. You might be asked to find the magnetic field strength given the force, for example. One point that we need to take note of, let's have a look at section BC. I want you to think about, what do you think the force on the section BC is at the moment? So pause the video, have a think. Okay, well, hopefully you have thought about it, and had you thought about it, you might come to the conclusion that side BC is in fact in the same direction as the field line. In other words, they are parallel, which means the conductor and the field lines, the angle between them is 0. Which means, and the sine of 0 is 0. Which means that in that case, for the section on BC, because the conductor and the field lines are parallel, the sine of the angle will be 0, therefore all of this will be 0. There is no force acting on length BC at the moment. So that's something you need to be careful of, and often in exams they will throw in a trick question like that, expecting you fully expect to calculate a force, where in actual fact the force could be zero. I want to take this idea of the force being zero on the end one further step, and so what we'll do, I will